Chapter 3, Vectors and Motion in Two Dimensions. Section 3.8, Motion in Two Dimensions, Circular Motion. For circular motion at constant speed, the acceleration vector A points toward the center of the circle. An acceleration that always points directly toward the center of a circle is called a centripetal acceleration. Centripetal means center seeking. Centripetal acceleration is just the name for a particular type of motion. It is not a new type of acceleration. A car is traveling around a curve at a steady 45 miles per hour. Is the car accelerating? A, yes, or B, no. Answer is A, yes. It is changing direction. Therefore, it is accelerating. A car is traveling around a curve at a steady 45 miles per hour. Which vector shows the direction of the car's acceleration? Answer is B, towards the center of the circle. This is centripetal acceleration. To complete our description of circular motion, we need to find a quantitative relationship between the magnitude of the acceleration A and the speed V. Let's return to the case of the Ferris wheel. During a time delta t in which the car on the Ferris wheel moves around the circle, from point 1 to point 2, the car moves through an angle theta and undergoes a displacement as shown in figure A. We've chosen a relatively large angle theta for our drawing so that the angular relationships can be clearly seen. But for a small angle, the displacement is essentially identical to the actual distance traveled, and we'll make this approximation. Figure B shows how the velocity changes as the car moves. Figure C shows the vector calculation of the change in velocity. The triangle we use to make the calculation is geometrically similar to the one that shows the displacement, as figure C shows. Remember from geometry that similar triangles have equal ratios of their sides, so we can write delta V divided by V must equal D divided by R. The displacement is just the speed V times the time interval delta t. Using similar triangles, we find that delta V divided by delta t is V squared over R. Since delta V over delta t is the acceleration, the centripetal acceleration is V squared over R. Centripetal means center seeking and points towards the center of the circle. A toy car moves around a circular track at constant speed. It suddenly doubles its speed, a change of a factor of 2. As a result, the centripetal acceleration changes by a factor of A, 1/4, B, 1/2, C, no change since the radius doesn't change, D, 2, or E, 4. The answer is E, 4. Since we've doubled the velocity, the acceleration has quadrupled. World-class female short track speed skaters can cover the 500 meters of a race in 45 seconds. The most challenging elements of the race are the turns, which are very tight, with a radius of approximately 11 meters. Estimate the magnitude of the skater's centripetal acceleration in a turn. The centripetal acceleration depends on two quantities, the radius of the turn, given as approximately 11 meters, and the speed. The speed varies during the race, but we can make a good estimate of the speed by using the total distance and time, which gives 11 meters per second. We can use these values to estimate the magnitude of the acceleration, or 11 meters per second squared. This is a large acceleration, a bit more than g, but the photo shows that the skater is leaning quite hard into the turn, so such a large acceleration seems quite reasonable. Turning a corner at a typical large intersection in a city means driving your car through a circular arc with a radius of about 25 meters. If the maximum advised acceleration of your vehicle through a turn on wet pavement is 0.40 times the freefall acceleration, what is the maximum speed at which you should drive through this turn? Using the definition of centripetal acceleration, the answer is 9.9 meters per second, or about 22 miles per hour.